This is the S.H.O drive's presentation on magnetic fields and energy. This is an Excel presentation, and I will show you slide by slide, or tab by tab in this case, or worksheet by worksheet, what this is about. So the first tab is basically an overview. This is the S.H.O drive logo. It's based on the S.H.O drive's coils, and just to show you what that looks like, this is the drawing of the S.H.O drive that I made a while back. This is a recent rendering of the S.H.O drive coil from a different angle, and over here is a older rendering. Okay, so just to look at those renderings, here is one example, but let's go ahead and view a different view. It's a different one. So this is the S.H.O drive coil. We'll go ahead and save this. Looking from different angles. So this will consist of two coils, two S.H.O coils, that will produce magnetic fields by having current pass through them. So let's go ahead and check out the the Excel presentation. So this is the screenshot of the S.H.O drive website. Okay. So, and this is the screenshot for the YouTube channel for S.H.O drives. Okay, so now let's just go ahead and view this. This is a screenshot from the magnetic energy article on Wikipedia. And right here we see that the magnetic energy in a magnetic field as an energy per unit volume in a region of space, defined by the magnetic field B and the permeability Greek letter mu down here. The magnetic field in turn is based on the curl of the magnetic vector potential. That's an operation on vectors, this triangle and the cross combined meaning curl. We have a product of this, which is a constant. This is the magnetic permeability of free space. And then this over here is a difference of two terms. Now notice there's a minus sign on this one. And this is responsible for the return lines of magnetic fields going around like this. Okay. Now this term over here is responsible for the radial components of the magnetic field because it has the vector r here, and it's multiplied by the dot product of two vectors, which means a scalar. But if you take a vector times a scalar, you get a vector. And this vector will point in or in opposite direction to the vector r for any given point. So for example, over here, we have a component of the magnetic field that is at right angles to the magnetic moment of this pair. So at right angles, that can only be explained by this term here, where this term helps to explain any components that are in line with the magnetic moment or in opposition thereof. So this portion over here, all these field lines along this axis of symmetry, if you will, that is caused solely by this last term. The first term here in this parentheses cannot account for that, particularly because this dot product here between the magnetic moment and the radial vector, in this case, those would be at right angles. So your radial vector would be, going this way, while your magnetic moment still goes that way. The dot product is based on a cosine between angles. So if the cosine of the angle is 0, because the angle is 90 degrees or 270 degrees or whatever, then this will return 0. But this will return a value at this position. So that gives you a general idea of what this term is about, or this value, the magnetic flux density. So the magnetic flux density comes from magnets, of course, or moving currents. Now, basically, there has been a question of how is energy extracted, quote unquote, from magnets, and there's a thing here about inherent kinetic energy associated with the electrons orbiting a nucleus. So this is what this answer is. This Michael Miller person here got the highest response on this question. There were 3 answers. He got the highest score. All right. So also now we have this page on rare earth magnets. Now the rare earth magnets have a relative permeability of unity. If it's the if you're talking about a rare earth permanent magnet, that's a type of permanent magnet. Now some permanent magnets do have a high permeability, and that includes such things like here he says alcino or steel magnets, which is the old technology. Now the new technology, which is more linear, is it involves permanent magnets that don't have a high relative permeability. Meaning, if you try to magnetize a permanent magnet in its default room temperature state, it won't change its magnetic moment, and so there won't be any alignment or realignment of dipoles inside a neodymium magnet that would cause, say, your back EMF into a coil. All of the back EMF would simply be self-inductance related to the coil and not related to any, say, neodymium magnets interacting with it. But if the neodymium magnet were to rotate inside, say, a S.H.O coil, then there would be induced currents as a result. Now, the direction of those currents being dependent on the induced flux through the loop and how it moves through. So anyway, in classical physics, the magnetic field of a dipole is calculated in this manner, so it's not like a quantum mechanical thing where it's really complicated. Here's your vector potential based upon the Lorentz gauge. That's without a T. But here's your magnetic flux density, which is simply the curl of the vector potential, whether or not it's the one from the Lorentz gauge. And so again, we have the same term here, and here's our unit circle diagram, including our degrees and our radians and our point coordinates, also our x and y axes, of course. This is the case of 90-degree orientation of the magnetic moment, which is represented by vector m. Okay, and so I have transliterated this equation into x and y components, which I will have then, which I'll then do in a later spreadsheet here. Well, I'll show you. I've already done it. I'm going to show you later. Okay, so this is a general overview of what this is about. This is about magnetic interaction energy density. Now that's kind of a mouthful, but basically what this is, when you have energy density based on the square of a value of a vector, let's think about it here. Let's go back to this page over here. Okay. Now this is based on the square of the magnitude of the magnetic field B. Now, if you take the magnitude of a vector, you can represent that as a scalar. So basically, the norm of the vector, so that's a positive scalar value. You square that value to get your magnetic field squared. So basically, your energy density is proportional to the square of the magnetic field intensity, or your magnetic flux density in this case. That's how you want to call it, because you can use the term magnetic field intensity to refer to a magnetizing field, which is related by a constant to the B field for, let's say, in the vacuum. So anyway, now this is similar to the the relationship between basically it's involving the cosines of angles. But the magnetic interaction energy density is positive when the vectors, the magnetic field vectors from two different sources, see the red arrows circulate the bottom coil here, and the blue arrows are circulating the top coil here. See that? So here's your top, which is over here, bottom's over there. Of course, it wraps around, but you get the idea. So there's this angle called gamma. Normally, you would associate it with C, capital C, this would be a capital C instead. This would, of course, be your side C. But here we're going to treat these sides as vectors. Here's two rays from this point spread by an angle C or gamma in this case. Now, we subtract that angle from 180 degrees, or pi radians, you'll get the angle between this blue arrow and the red arrow. So the acute angle pi minus gamma between the vectors b1 and b2 is that. Now, if I took that into consideration, that the cosine of this angle is positive. So if I take something based on 2 times, or let's see here. You see how you have an area of this parallelogram that's minus AB cosine gamma. But we are choosing a vector, B2, which is the opposite of B. Here, well, this is capital B. The capital B here refers to the magnetic field B, but the lowercase b and the lowercase a, those are referring to the sides of this diagram. So we kind of have to translate this somehow. Okay, so over here is your negative magnetic interaction energy density. And basically, we have an obtuse angle between pi and gamma instead of an acute angle. So this would be gamma in this case on the right. In this case on the right. But here's your obtuse angle over here between the red arrow and the blue arrow. Now, these are coded red and blue to reflect what's going on here in the picture. So here's your positive magnetic interaction energy density from these arrows that are spread by an acute angle. Here's your arrows spread by an obtuse angle in this red circle here. Now you can see, by looking at this, you got this a squared and the b squared and your c squared. If you take the area of and adding this area, okay, you should get a value so you'd have to add this and this, 2 of these, and a squared and b squared together to get the area of c squared. So these areas essentially represent the magnetic interaction energy density that basically makes the sum greater, it makes the whole greater than the sum of the parts. So a squared and b squared are the parts, but the whole is c squared. Okay? The opposite is true for negative magnetic interaction energy density, in which case you're basically doing the whole is less than the sum of the parts. So here's your whole, which is less than the sum of the parts. And in this case, now just consider that this gamma, the cosine of this gamma, is opposite of the cosine of pi minus gamma. So if I were to substitute pi minus gamma here, this sign would drop, this sign would drop. So this would be positive and that would be positive. But let's say we try to apply the same thing over here. Now this thing acquires a negative sign. And that's reflective of the fact that the whole is less than the sum of the parts. Now, let's think about it like this. Here, this triangle matches that triangle, and that triangle matches that triangle, and that triangle matches that triangle. So you have this plus this equals this plus this plus this. over here, all right, so almost an hour has passed, and I have a 15-minute limit on my free Screencast-O-Matic recorder for my desktop. So, all right, back online. So, again, here on this side, the whole, c squared, is greater than the sum of the parts, a squared and b squared. The difference being the areas of these two parallelograms. However, for the case of negative magnetic interaction density, this whole is less than the sum of these parts. The difference being these two areas. Okay? So going back to here, this plus this plus this plus this equals this. Whereas this plus this equals this plus this plus this. Okay? So, again, looking at this diagram here, we see there's a green circle containing a region where the magnetic interaction energy density is going to be positive based on an acute angle between the vectors b1 and b2. Well, let's just look at an example. Here is, that would be b2, I believe. Yes, that's blue. And going back to there. So there's your b2 vectors from, which one this is? S.H.O coil 1. So let's say I were to vanish this field. That was my keyboard. Okay, so obviously there's no more field there. And here, there are fields there again, right? And I selected 440 because that's going to be the number of ampere turns if there was like 2 amps going through 44 turns. Excuse me, through 22 turns. So this coil, S.H.O coil 2, has no current going through it. All right, so let's say if I had 2 amps going through the other 22 turns that the S.H.O 2 coil would have. So S.H.O coil 1 would have 22 turns, and S.H.O coil 2 would have 22 turns. This is just an example. Okay. So anyway, let's go ahead and go to this one. So here's our S.H.O coil 2. Here we vanish the field. Like so. Right. Did I say 2 amps? I meant 20. Anyway, so if you had 20 amps going through 22 turns, that would be 440 ampere turns. Anyway, so here is an isometric view of the S.H.O coil. Let's go ahead and change our display. Go to a more perspective view, so I gotta zoom in now. So here's our perspective view with the vanishing point somewhere at a horizon that's a finite distance away from our view. So let's say we take this to the extreme. There's this really, really, really twisted angular version thing of this. Going back to isometric. It's like that. Kind of like Roller Coaster Tycoon used to be. Versions 1 and 2. Isometric. So, okay. Let's go ahead and load this up. And next tab. So, alright, here's our little video game. We can move this magnet closer. And there we go. Move it further away. Move it back. Move this back. Oops. Okay, so here is our way of calculating. This is for the magnitude of the magnetic field energy density of two dipoles in Tesla units. So how does this done? Well, that's based upon the way of doing the code. Here's for the X component of the magnetic field. So going here, there's the magnitude of the B field, which is based upon this. Got the square of C37. Where is that? There's C37 right there. And then we've got divided by twice the value of this, which is our magnetic permeability, which is in henries per meter, 4 times pi times 10 to the minus 7. Okay? So energy is also stored in the magnetic field. The energy per unit volume in a region of space of permeability mu containing magnetic field B is U equals 1/2 B squared divided by mu. Mu. Okay? So, all right. Now, I have the dipoles superimposed, and since they have the same magnetic moment, they will generate the same contribution to the magnetic field. So if I were to render this 0, these values should all reduce by a factor of 4. Okay, so for example, this is 2 times e to the 2, which is 2 times 100, which is 200. Well, technically, let's see what this really would be. So 159. It's rounding. Okay, 159. So let's go ahead and pull out our calculator and see what would happen if we remove the dipole. We divide that by 4. It should say 39.75 or thereabouts. 39.75. Let's see if our prediction rings true. Let's get rid of this dipole. Okay, 4 times e to the 1, so somewhere around 40. Let's see if that rang true. 40 is our answer. So it's somewhere around those lines. So again, let's go ahead and push this one back up. 159. So, just take 159 divided by 4. Okay, that's 39.75. I'm not sure if I said that earlier. Maybe that's what I said. But because I take that times 4, 159. Okay, so there's evidence right there. Now, here is the average of the energy density. Now, if I get rid of this, this value should drop by a factor of 4. It looks like it. Okay, so what happens if I move this away, the one on the left away from the one on the right, but not enough for it to leave the screen? So I will be counting both. So I should then see this value drop by a factor of 2. There. It's dropped by a factor of 2. And slightly different. Slightly different. Now, since it's going off the screen, at some point, it's half. Okay, so this is now showing only the magnetic field of one dipole. So this is 10545. What if I move this further? It barely changes because it's practically off screen. Okay, I can increase this till, I reach this point. Let's go some more. Okay, 1.0532 e to the 00. Let's drop this back and then vanish this. 1.0532. So it's like it wasn't even there. Okay, let's spread this out a little bit. Okay, so this was P2 times -1, and then this obviously would be, because I'm not supposed to type directly into that, drag this thing over here to this little thing. There we go. That's more like it. Okay, so if I make this 0, that's the way to do it. Okay, so there is my minus 0.2 of x coordinate. Now as I move this out, let's move that into the negative 0.6 x position. Let's do the same thing for the other. Now they're separated by plus or minus 6 on the x-axis. Okay. Now this says 100% aligned. That basically means that these two sources of magnetic field are pointing the same direction. Now to see that, okay, so these average the values at z equals 0. Okay, so just because the x field average here is positive doesn't mean it would be if we considered all 3 dimensions. In fact, it would have to be 0. Okay? So the x component of the magnetic field B of 2 dipoles in Teslas or T. Okay? So the green area represents where the x component of the field is pointing to the right. That is to say, the positive x direction. Whereas the red regions represent where the x component of the magnetic field is pointing in the left direction, or the negative x direction. Okay, just like in our unit circle. Here's our x direction, here's our y direction, and then the opposites, of course, are on the opposite side. That's the x components. Now what about the y components? Well, if I have magnetic fields going to the right and they split apart, going around back, like so, and same with this one, going out this way, going around back, then we would say, as a prediction, that the y component of the magnetic field B would be green over here, or if that's to say in the positive y direction. So here's your 0, 0. Here's your y equals 1, and this is in meters. This is x equals 1 in meters. Okay, so just going down, well, here, there's our green area and our red area. And it also reverses around each dipole. Now, this will be this shows the second dipoles only, its x component, and then over here is its y component. Okay, and this is green again because the y component of that magnetic moment. Imagine a magnet pointing from left to right. So the North Pole would be here, and the South Pole would be here. Okay, this is for the x component, and this is for the y component. So here's the interaction field energy density between the first and second dipoles. Now here they're aligned. So we have this green area, which is positive, and we got this red area, which is negative. Okay? Now, I have a positive average for the interaction field energy density. And this is in joule per cubic meter. Okay? Now, this is calculated based upon the square of the total magnetic field minus the square of the first dipole's magnetic field minus the square of the second dipole's magnetic field. That's in turn divided by twice the magnetic permeability to give me the interaction energy density of the magnetic field, as shown on this equation. If there's an error, it returns this. Otherwise, it's all good. Squaring C37 minus C63, So basically, this would take C63, which is our x component of the magnetic field B, of the two dipoles, minus Alright, so about 40 minutes or so has passed. I had to go through another recording. I saved it. Now that it's saved, let's go ahead and make another recording. Okay? Part 3. So back to the interaction field energy density in joule per meter cubed between the first and second dipoles. Now, let's look at the equation here. We've got B total squared. That's the total magnetic field squared. That is to say the norm of that squared. But we also have the norm of the first dipole's magnetic field at a given point. Let's say this is, okay, x coordinate -1 meters, y coordinate +1 meters. Okay? So calculating the magnetic field, let's look at here. So C37 squared. What is C37? C37 is the magnitude of the magnetic field B of the two dipoles of x coordinate -1 and y coordinate 1. So let's just go ahead and look at this equation. So that is quite a mouthful, actually. We've got all of this. Here's an if statement condition. If that if statement is satisfied, it returns a blank. And this basically means, for example, okay, let's go ahead. Where is this? Okay. Let's select the actual one. There is C37 right there. Okay, that's C37. This returns the square root of C63 squared and C89 squared. So C63 squared gives me this x component squared. So you lose the negative sign, you're squaring it, and then we'll add the other, the y component squared. And this is basically Pythagoras' theorem. We take the square root of that, we return the vector that basically forms the hypotenuse between the x component and the y component. That gives us the magnetic field vector magnitude, so as represented in C37. Okay. Now going back down to here, and it might just help to highlight this. There's a way to do this, formulas. So trace dependence, or precedence. Okay, there we go. All right. So there are my dependence values. A lot of them are just C variables, C37, C63, C115, so on, and then we have our D value here, our magnetic permeability at cell D2, which is in our denominator, but everything else is in the numerator, and they're all being squared. So C63 minus C15, well, the C63 gives us the x component of the magnetic field B at this coordinate, -1, 1. Okay? So that's C63, and C15 brings us down here. X component of the magnetic field B, but this is only for the second dipole, okay? Which I have set at a fixed value of 0 degrees, okay? The 3 o'clock direction, okay? And so that's the x values, and the y values are the same way over here. Squaring those. Then subtracting also the x and y values for the second dipole. So for the first dipoles, x and y's, and the second dipoles, x and y's. As shown in this equation, B total squared b, okay, so it's minus b first squared minus b second squared, then divided by 2 times mu down there. Okay? So that gives us the interaction energy density of the magnetic field. Now, at here, we got the x component of the magnetic field B of a dipole, as well as the y components. So basically, this logic comes from this equation here, our magnetic field B as a function of vector r. Okay, so vector r is it's got a magnitude and a direction, and that direction here would be indicated by an angle. Okay, so that is based upon the angle of the sample, the sampling point. So represented by theta underscore samp. Okay, and the angle of the magnet's magnetic field, as represented here, in this case it would be 90 degrees, or you have the magnetic field's magnetic moment, which generates that based upon this. So something interesting about the magnetic moment is it's not proportional to the magnetic energy, but it is more or less associated with a charge combined with its magnetic, the angular momentum. Okay, so you think of like rotational kinetic energy that depends not just on the angular momentum, but also the angular velocity. Combined with that, divide by 2, which gives you a rotational energy. But anyway, and this would be a way to explain why magnetic fields don't necessarily disappear if, or let's say like say you take some rotational kinetic energy. That doesn't mean you're using up the angular momentum, because it's not strictly dependent on the. So whatever. Okay, so the point is, we have highlighted this here in green in yellow text, which corresponds to this part of the code. Now this is a way to space it out. Here's our if statement that I talked about earlier. I did talk about that earlier. Okay, so that if statement, basically, these white squares, let's see here, for example, in these white squares, you have L1 is at this coordinate, so if this plus, let's say G61, so G61 is this squared, and this here, this is our value A73, which is 0, that squared is less than 0.001, or this here, R1, which is over here, minus that, like so. So that would apply for this case. So this cell over here satisfies that condition. This cell over here satisfies this other condition. Okay? So, now the idea with that is, I don't want like values here that are basically you're almost dividing by 0 to show up here. These would be like infinitesimally close to this point. So let's say I drop this condition entirely. So if so let's say we drop that entirely, and we'll undo this. We don't want to keep this like so. And obviously this is unacceptable, dividing by 0. So obviously that didn't make sense. That's why I have that condition in place. Okay, but we're averaging the x components here. So let's just go a little bit forward. I might have derailed myself a bit, but here's a condition where the first dipole is rotated at 0 degrees. 90 degrees, and it's 0% aligned with the second dipole. And what does that mean? You're basically taking the cosine of the difference between the angles of the first dipole and the second. So what happened? Well, I see here the interaction energy density has it has dropped. So here it's representing that it's, well, here the yellow represents that the interaction energy density is essentially 0. Now, because of your floating point errors and, other like things about, how you're selecting things out of a square sample group here or whatever, it gives us, not exactly a 0 value for the interaction energy density. So let's just go ahead and click this link. That takes us back down here. Now we have a situation now that we have, let's go ahead and change this a little bit. Now it's negative 100% aligned, which basically means that it's in opposition to the second dipole. So our interaction energy density is negative. That means, in this particular case, it's the same thing as this side. So here's our whole, here's our parts. Okay? All right. So we have rotated that. We can, of course, rotate it some more if we like. Okay. So, that's pretty much it for that. We'll just go ahead and look at here. Here's the energy density of the magnetic field. So this would be the whole. So this is just C37 squared divided by twice the magnetic permeability. And that's there. So the magnetic field B, and we take the norm of that, we square it, we divide by twice the magnetic permeability. Okay? So, so the field average in Teslas, whatever. Okay? And just to look at that here, the 90 degrees, same as the 12 o'clock direction, as an analogy. It's up here. And so we should see that reflected on this dipole, which is also vertical. Now if we try to make it, let's say we make it, 9 o'clock. There's pointing in the 9 o'clock direction, as indicated by the negative space in the middle here. Whereas this one here, the second dipole, is pointing in the 3 o'clock direction. Okay? Now if I rotate this, and this is the x component here. Let's look at that one. So we have a magnetic field going up like this, then pointing left and right, then turning back around, pointing right here and pointing left here, then pointing back up, which would, the up part would be showing here, where if it points up, it then goes down, goes back up again. Right? So let's say we drop this one over here. There it is. This is how wide it would be. It would go up over here, all of it's over here, then goes back down, and back up again. Okay, so now for the last one. But first, let's just go ahead and check this out. Okay, it's a negative interaction at energy density. Yeah, I did go through this. Positive. So, one more thing. Here it says positive 1.8672 e to the minus 3, and that is in joule per meter cubed. Now it says 1.8672 e to the minus 3, which is the same thing. Okay? And likewise, in the middle, it's going to be negative. Wrong. The actual middle. Actual middle. That middle. Negative 1.8672 e to the minus 3. Okay? Now you can see how that works. Here is the dipole in a uniform field. So in this case, we get the magnetic moment of a point dipole at the origin. 100 ampere meters squared. Now that's a value of magnetic moment this is also equivalent to 1 times e to the minus 4 Weber meter. Okay. Now, here's the dipole in the 3 o'clock direction, and we got a Alright, so a certain amount of time since my... Okay, so that was 8:57 p.m. Now it's 9:52. So I spent some time reviewing the videos. So let's go ahead and finish this. Okay. So this thing here, I said that this was equivalent to that, but what we'd have to do is we multiply the ampere meter squared value with the magnetic permeability value. So it's ampere meter squared times henries per meter, which will give us Weber meters. Okay? So here I've got the dipole here. It's already rotated to the 90-degree orientation, which matches this. Okay, so here, let's blow this up a little bit. Here is our magnetic moment M. Okay? Our magnetic moment M is considered a constant. We're not changing this. So you can imagine a tiny permanent magnet with a fixed amount of magnetic moments. And that is something like, if you'd imagine, this has a value basically equivalent to what would you get if you had 100 amps going through a circular loop of an area of 1 square meter. That's where this comes from. Okay? 100 amps in a loop, a closed loop, and it has an inside area of 1 square meter. Or conversely, 1 amp going through a loop of an area of 100 square meters. Or say 10 amps going through a loop of an area of 10 square meters. Then when it's multiplied by the magnetic permeability, we get this other version of the value of a magnetic moment for a dipole, which you see is you combine a unit called Webers, which is units of magnetic flux, multiplied by a unit of distance. This is similar to, take an analogy, the electric dipole moment, which is measured as a product of the charge and the distance between the charges. So anyway, we have an external field strength now of 100 ampere per meter, but it's at 90 degrees to this dipole. So what happens if I slightly align the dipole to the external field? So right now this is at a 12 o'clock direction, and this is the positive direction, which is the same thing as the 3 o'clock direction. So it's at 90 degrees, so let's say I start moving this closer to the x-axis, so down some. So now we're at the 12-20 direction. Now you see here that this interaction field density, interaction field energy density between the dipole and the 1.26 Gauss field is positive. But if we were to turn this around, we'd see now we've got a negative interaction energy density. Let's say we double this value. What happens to this value? This should double. So it should say something like 1.8 e to the minus 2. Let's say if that's true. Okay, so it's actually 1.93 e to the minus 2. So let's take that thing, 1.9308, and divide by 2. Now bring this back. Now we have 0.9654. So pretty much in the ballpark of the calculation here. So yeah, let's go ahead and rotate this back. Okay. So let's say we get rid of this. So there's no interaction field energy density when you've got no external field strength to interact with. Let's bring that back, but let's get rid of the dipole. Now we're back where we started. Again, no interaction field energy density. There's no y component to the magnetic field at all because the external field is purely in the x direction. Here is the x component of the magnetic field B. We see here there is an x component to the external magnetic field as dictated by this. So this is, oh, that's the logarithm. This is a way to make the color scheme better, but really the value is over here. And what we're picking up is simply this one. All this other stuff doesn't show because here my value for this is the magnetic moment of the dipole. I have set this to 0. Now it's L. That's at L2, and so this is 0, and so this whole thing becomes 0. Okay, so we had this. So let's say if I was just to hypothetically bungle this up and I make this negative, what happens to this cell? Well, here we've got a negative value, like so. It's -1, right? Now, let's see here. There it is. So negative, oh, so that's, well, here in this green one, it's 1.257. Okay. That's matching the Gauss value. So this is the x component in Gauss. That is, if you take 10,000 Gauss units, that's equal to 1 Tesla unit. Let's look at this one. So remember, I changed here. I made this negative. Now it says negative 1.6. I mean, no, negative 1.257. Da 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 da. Same here, except without the minus sign. Da 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 da. Okay. So let's just undo that. All right. So let's drop this to 0. Now we don't have any of these, and it has a problem calculating some trend lines here on to the right. So let's see what these trend lines are about. Let's go ahead and bring back our magnetic moments. So we see here there's this thing I call the box average for the energy density. So let's go ahead and trace our formulas. Precedence. Keep that there. Okay, so basically for each of these cells, I summed the contents of this to get that value, and I summed the contents of inside this box to get that value. I took the difference between those two values and I divided by, let's see here, this average is based upon, I've got, alright, so I had to stop the previous recording a little bit early because I actually had the equations on this section here, they were correct. I started to think that I did it wrong, but it wasn't wrong. So let's go back over here and see a replay of this.
So we see here this is thing I call the box average for the energy density. So let's go ahead and trace our formulas.
Okay, so what this does is these precedents trace back what was used to calculate, in this case, the average column. So we have here a difference. Let's go back to here. So here's our average based upon dividing this difference by the number of cells in a ring. Now I was starting to think, oh wait a second, I'm doing this wrong. But no, it's not. Let me go ahead and show you where this was supposed to be. Okay, so that's the first step. So we have AW24 divided by AX24, which gives us the difference divided by the count. So here the difference is the difference between these sums. So this sum here, let's go ahead and trace this further back. Let's just trace this one back. Precedence. Okay, so we have the difference between these two sums. So this sum, trace this back, is the sum of these 9 cells. Now, because the middle cell is 0, it's basically blank. So the sum is the sum of all of these values. So if I selected this, I would have 4 times e plus 4 times 10 to the 2, or it's 4 times 100 thereabouts. Okay, so that would be our sum of that one. Then the next one, it's slightly more. It's 5 times e to the 5 times 10 to the 2, which would be around 500. Okay, so now every time I go from here, so first you have 3 here, then you have 3 here, and then you have 1 here and 1 here. Then if I go to the next ring, here I have 5 here, I have 5 here, and I have 3 here and 3 here. So each of those segments increase by a count of 2 cells. So for all sides, that's a total increase in the number of cells by 8. Okay? So we're dividing by 8 for this average of the center, dividing by 16, then 24, then 32, and 40. So this one has 7 on that side, 7 here, and 5 over here, and 5 over there. So we end up with an average that has a profile based on, it varies by the inverse 6th power. Now, where does this come from? Well, we're squaring a value based upon the magnetic field. Okay, so the magnitude of the magnetic field B is squared in the process of getting the answer for the energy density in the magnetic field. So the magnetic field averaged around here. Let's go ahead and trace this one. Now you can see it's the same process, but now this is taking the average of each of these rings, and then same here, and so forth. Okay? So with that, this gives us a value that tends to vary with the inverse cube of the distance, which in fact is how it is. Now, let's go ahead and check out something here. All right. We see here we have an inverse cube value for this. But what about this one? Here we have an inverse to the fifth. But we also have in here the magnitudes in the directions, because we have these vectors, right? Here's the radial vector, and if I were to double the magnitude of the radial vector, it would affect not just this, but the value of this this dot product of these two vectors, the magnetic moment vector and the radial vector. So this numerator here would increase in proportion to the square of the radial vector, but it also would scale in proportion to the cosine of the angle between the magnetic moment and the radial vector chosen, and that would be there. So this is where we'd have this basically, since it's based on an inverse cube, when you take that into account, we're taking this the square of the x distance and the square of the y distance and raising that to the 3/2 power. Okay, so if we took the square root of this instead of 3/2 power, we would have the magnitude of the r vector. But we take the cube of the root, then that would be the 3/2 power, which explains this. Okay, and we have a situation if the magnet is rotating, then the x and y contributions of each of these terms would rotate with it. So when the theta mag is 90 degrees, this value here would actually be pointed in the direction of 270 degrees, this term with the minus sign. So, for example, so that would be the y component, and so if theta mag equals 90 degrees, this one would be equal to 1. This would be equal to 0, so it would be all based upon this. Now, if the sample is being measured at, let's say, here or here, then the cosine will be at an extreme. So in the case of this angular difference being 0, then this cosine, which is squared, you have the cosine of 0, which is 1, and you square it, it's still 1. So that becomes 3 minus 1 times 1 times this divided by that. So you end up with a situation where you've got a positive y value for this. But if we have a situation where the sample angle is opposite of the magnetic moment's angle, then this this would be actually this would be pi, but we would still be squaring it. Times 3 minus 1, still get 2 there, and the rest is the same. Which makes sense, because as you can see here on this magnetic moment here, the field lines that point up here also should point up over there. So that seems totally correct. So we'd see that this field is supposed to drop inversely with the cube of the distance, generally speaking. And so if we square that, that value would vary with the inverse 6 power, or inverse 6 power of the distance. So, or the negative 6 power of the distance. And so that's what we get here. All right. And when this is interacting with an external field, notice here, if it's 100% aligned, our interaction energy density is going to be positive. Now, if I rotate this to 90 degrees, now you see it's practically zero. Now, once we rotate it in the opposite direction, our interaction energy density is going to be negative. Okay? Now, what happens if we integrate this all over space? Well, the average magnetic field integrated all over all positions should be zero due to symmetry. Okay? Or rather, let's try this. The divergence of the magnetic field should be zero. Okay, so it's what they call a solenoidal field. So every line of flux that goes to the left is going to have a return path. So the right cancels the left, the up cancels the down, the forward cancels the back. So all those things cancel. So technically, all of the left fields and the right fields, they cancel. Okay. But that doesn't mean the interaction energy density will cancel. Because, let's say, for example, we have these pictures. And so, pictorially, this area represents the interaction energy density associated with when you have, let's say you had a constant field, a uniform field, just like we have here, representing this square and this square, right? Just the sizes of those squares. But here, we got an arrow going from the bottom left to the upper right, and then another arrow going a little bit to the lower left. So we end up with a square of this size representing the square of the net magnetic field. Whereas with this one, we're adding that value, because again, you'd have to have equal and opposites here, like so. And of course, like here, and the thing with external magnetic field, the idea of having a perfectly uniform magnetic field to infinity doesn't make much sense. Let's just look at this one, for example. Let's say we had, because in the end, all magnetic fields are coming from somewhere. So even if we had this thing, it has to come from somewhere. So let's say we did this a little bit less extreme. That's just for the second only. So imagine there's just like a really large magnetic field from far, far away. So that's what it really is. But, in the end, it's basically the same thing as what we have over here, the interaction energy density, working with these shapes. So in the case of a positive magnetic interaction energy density, the whole is greater than the sum of the parts. And for a negative magnetic interaction energy density, the whole is less than the sum of the parts. And the differences are reflected in these parallelograms. Okay? So in the end of the day, this is basically a calculator to give a sense of what the magnetic energies associated with magnetic fields are. So I'd like to thank you for your time and have a great day.